So yes, I'm going to talk about my existing and evolving ideas on how the first continents formed and how the early Earth might have behaved. And by early Earth, I really mean anything before 3 billion years. So the cover slide here is, as people that know me are very well aware, because I go on about it all the time, is my favourite place on the planet. It's the Archaean complex in northwest Scotland. It's a rather typical fragment of Archaean continental crust. It comprises TTG gneisses, which, so for those of you that aren't experts on Archaean things, I'll explain terminology as we go, hopefully. So these paler rocks in the background, interspersed with various volumes of these dark coloured rocks, mafic, ultramafic bodies. So rather simple, and you'll see those sorts of rocks if you go particularly to the deeper levels of Archaean crust anywhere on the planet. So let's just have a discussion of a little bit of a timeline. So in the beginning, at least of our solar system, so the oldest known solids we know, these so-called calcium aluminium inclusions that we find. So yes, these calcium aluminium inclusions, 4.567 billion years old. The Earth then accreted around about 4.54. Some of these numbers are debated, of course, like almost everything I'm going to say. So around 4.5 billion years, probably, maybe a bit later, the Earth collided with a Mars-shaped object here, ultimately to form the Moon. And the Moon was probably a complete magma ocean when it formed, and the Earth certainly, or almost certainly, would have had a magma ocean of unknown depth. So our oldest Earth materials are the Jack Hill zircons. They're around about 4.3 billion years old, at least the oldest ones. And then the oldest rocks we know, or at least the oldest evolved rocks from which we can find zircon, are the Acasta gneisses, and the oldest components of those are 4.03 billion years. And then around about 3.8 billion years ago, the bombardment of the Earth and the Moon and the inner solar system by bolides died off considerably. Now, whether or not there was a late heavy bombardment at this time, who knows? And around about the same time, 3.8, 3.9, we see the widespread appearance of felsic granitic rocks on most cratons, and I bet we keep finding more of them as we look. So essentially this talk is going to be about how did we get from the left-hand image, crystallization or ongoing crystallization of the terrestrial magma ocean, to the planet we know and love today, with its oceans and its continents and its subduction zones and plate tectonics. So anybody who's been lucky enough to spend some time in some Archaean terrains will know that Archaean rocks are different to younger rocks. So as I explained earlier, this is the archetypal, I would argue it's the archetypal part of our locality for Archaean crust, at least upper Archaean crust, and it's got these so-called dome and keel morphology. So we've got these red blobs here, which are the granite domes, and they have, particularly the early ones, a very characteristic sodic, low potassium composition. So they're mainly tonalites, trondhjemites. There's some granodiorites. They become increasingly important with time. So we call those rocks collectively TTGs. And they've been around for a very long time, so they're variably deformed and metamorphosed. And then in between those, these keels are dominated by basalts. There's some komatiites, particularly at the base, And then we start seeing the appearance of various types of sediments, both chemical and plastic. And we do find some aluminium-rich sedimentary rocks, but they're usually rather uncommon and usually rather thin. And we might come back to that later if I have time, and Luke is kind with his previous statement of the strict time period. So what do we know, in inverted commas, about the Archaean? So as many of you will be aware, it's a very strongly argued part of Earth history, purely because the rocks are so old, they've been smashed around so much, and we do have a mechanism of recycling things, plate tectonics, today, so it's pretty difficult to disentangle some of what the rocks are telling us, which is part of the fun, of course. But I think the majority of people would agree, the vast majority of people would agree, that these sodic granites, these TTGs, most of them were produced from partial melting of hydrated, low magnesium basalts, or gabbros, or whatever you want, mafic rocks. So as metamorphic petrologists, we call those rocks amphibolites. So they're mainly hornblende, plagioclase, bit of quartz, a little bit of something else. Nice straightforward rocks. So we can see on the right hand side, this is again is from the Leucine complex. We can see these dark amphibolites, and we can see the in situ formation and melting of these to form these sheets. And these sheets, you go and analyse them, they're absolutely indistinguishable from TTGs. So most TTGs, not all, but most, have this typical pattern that you can see down here in the bottom right corner. So they've got nice evolved patterns. So these are moving from things that are very incompatible to things that are more compatible. The rare earths here down the end. They've got this really characteristic signature of heavy rare earth depletion. And the only way of doing that is to have another mineral in the source rocks from which they were formed that likes to suck up those heavy rare earths. And that mineral is garnet. And if we looked more closely at some of these rocks here, you would see that many of them do contain garnet. We could also say that Earth's mantle was hotter in the Archaean. Exactly how much hotter is one of the many things that people argue about. And we can also say that the Archaean Earth was mostly covered in water. There may have been a few volcanoes sticking up above above the water, but they would have been very few and far between. So those are the things I think we can mainly agree upon. So I'm going to frame this talk, or try to, around 4 of what I see as the outstanding questions. And of course, those outstanding questions are all intertwined into the big picture of how things work. So those questions are: how much warmer were mantle temperatures in the early Earth? And by the way, I'm not going to provide any answers to many or any of them, just my biased view. So how much warmer were mantle temperatures in the early Earth? This second point is the question that absolutely everybody asks when anyone gives a talk about TTGs, for example. Where did the water come from to make them, to hydrate those basalts, to form the amphibolites? In what geodynamic setting did most Archaean, and I'll be talking about early Archaean continental crust form? Was it a subduction? Does that mean that there was plate tectonics? Or was it via some other mechanism? And the last point is: when did the first stable continents form? And of course, it's a hard problem, which is, as I said, one of the reasons that many of us are interested in. It's fun because you can get away with quite a lot more than you can get away with when you talk about younger rocks, because there's less evidence. And that's shown nicely in this really nice diagram by Taras Geria. So we can look at things at the surface. So this is depth, and this is time going backwards on the x-axis. And we can look. We have lots and lots of data currently, and we can also do lots of various geophysical. Generate lots of geophysical data, what allows us to probe right the way into the depths of the Earth. But of course, we can't do that going back in time. we've got rocks that are now exposed at the surface that we can collect, or maybe we can drill down a little way. And of course, those rocks have themselves come to depth, but from depth. But in the majority of cases, we're probably only looking at rocks that were in the uppermost couple of tens of kilometers of the Earth. We have some mantle xenoliths that may have come from a couple of hundred kilometers. But other than that, most of this vast green area we don't have any data for. So it's a hard problem. I've just added the L there for any of you that mistakenly think modelling only has one L. So I'm going to make a bit of a case that numerical modelling is really the way forward in addressing some of those questions that I have asked. Of course, as we all know, processor speed for computers is increasing exponentially. So those numerical models are becoming increasingly sophisticated. But of course, if you put rubbish in, the parameters that are required of these models, if you put rubbish in, you're going to get rubbish out. So the way forward, particularly for the Archaean or early Earth studies, is a cross-disciplinary collaborative effort whereby people with all sorts of expertise are making sure that the parameter space that the models work on is being fed with sensible data. So let's frame a couple of those questions. First of all, how hot? So both data and common sense will tell you that the Earth must have been hotter in the past. So the Earth's heat budget at the start came mostly or entirely due to its accretion. And then we can subsequently add heat to the Earth by smashing it with impacts, which of course have declined with time, as I said previously, and they were probably particularly intense before 3.8, 3.9, and those include the moon forming impact. So we can envisage what is called a multiple magma ocean origin in the early Earth, where things just keep getting remelted to various depths, depending on the size of the things that's hitting them. And of course, radioactive decay is our other source of heat, and that has decreased with time. Of course, that's what the word decay means. So if we look at when the Earth formed, or at least after the moon formed, we can see that the heat production today from the various radiogenic isotopes is around about 4 to 5 times what it is currently. So all this tells us Earth must have been hotter, but how much hotter? So we can look at some data as well. We can look at this. So this is very, very, I hesitate to use the word famous, but it's very well used and thought over data from a great paper from Claude Herzberg back in 2010. And he took what was then a very large database of basalt analyses and filtered them very carefully to try and constrain which he and his co-authors regarded as primary mantle melts. So primary crust, you might want to call it oceanic crust. And you can see that the compositions of those, out of the thousands or tens of thousands of data points, this was all that he was left with, kind of define a peak somewhere in the Meso-Archaean, perhaps, if you believe this fits, and some variation in the temperatures. So whereas today's mantle, this is Morb, is around, say, 1350, this mantle potential temperature, let's not go into what that means. It could have been a couple of hundred, maybe 300 degrees hotter in the Archaean. But as I say, this is argued about, and people question the validity of this data. So what are the consequences of a hotter mantle? A hotter mantle melts more, so the basalts that are extracted from it are more magnesium. So these are really quite extreme magnesium contents. So chromatites are 18% H2O. And that crust would have been much thicker, potentially up to 40 kilometers in thickness. So why is mantle temperature so important? Well, this is the first glance at one of these models. This and almost all of the models I'm going to present by Elena Sisova from various papers over the years and colleagues. And she showed really nicely that she could set up a model that seemed to reproduce subduction using a mantle potential temperature similar to the modern day. And if you believe the modeling, and many people don't like modeling, which is fine, as you increase temperature, you can still get subduction going at 100 degrees warmer than currently, but once we get to 150, 200 degrees warmer, subduction is very difficult to maintain, to start and maintain. So you have the essential problem is that your downgoing slab just becomes too weak to maintain any coherence. So it might start going down, but it should fall off before you establish anything looking like a proper subduction zone. So that's the first question I haven't answered, how much warmer. Let's move to how. So how might our early continents have formed? So here's a cartoon. This brown stuff is our mafic rock, and let's say it's hydrated, and we'll come to that in a minute. How do we melt that, or partially melt it rather, to produce these sodic granites? So one way of doing it is hitting it with impacts, and that is going to produce melt at a relatively shallow level. So there's going to be no garnet stable. So our garnet inline is shown here. This is the normal solidus crust that is not being impacted. So we can melt crust from impacts, but we've already said the majority of TTGs have got this heavy rare earth depletement, garnet in the source. That doesn't explain the vast majority of TTGs. We can melt in the mid-crust. That requires high ambient geothermal gradients in the crust, and depending on composition, you would expect little or no garnet. So again, we have a problem with producing most TTGs. So that leaves us with the majority of those rocks being produced by partial melting in the deep crust or the subcrust below. So that requires more modest temperatures and a mechanism to get it down there. So here's a nice diagram of some end member ways in which it's very easy, or it's a plausible mechanism to get basalt, which is hydrated, down to depth where it will melt. And the obvious obvious way of doing it is subduction. So we have our oceanic lithosphere here. We've got the crust, which is hydrated because it's underneath the water, and there's hydrothermal circulation. We subduct it beneath the continent, and rather than dehydrating as it does almost everywhere on the planet today to flux the mantle wedge and produce arc basalts, in a warmer Archaean, you could envisage the slab melting directly to produce TTG. So that's a good way of doing it. You might envisage that you might not get steep, I mean, this is not particularly steep, but a modern style of subduction, some sort of proto-subduction or shallow subduction, or whatever you want to call it. But that's broadly the same mechanism. But the other plausible mechanism of doing it is to melt the base of thick oceanic plateau-like lumps of crust, potentially above plumes. But whether by mantle plume, a mantle plume, what people mean by mantle plume in the Archaean, is not clear to me that it needs to be the same as a mantle plume as it's meant in the more modern context, which is something that is generated at the core mantle boundary. I personally don't think that there is a requirement for that, but that's not a fight I'm going to get into. So an important point to say is that whilst all of those mechanisms is a good way of making TTGs, and I think any of them is plausible, going back as far as you like in time, Subduction does not mean plate tectonics. So in the original definition of Tuzo-Wilson, excuse me, in '65, he was talking about various mobile belts, by which he meant the subduction zones and the spreading ridges and the transform faults, and made the point that they are connected into a continuous network of mobile belts. And a more recent paper looking at these sorts of things, these definitions, is a global network of narrow plate boundaries is a critical condition for plate tectonics. So subduction is not the same as plate tectonics. But when plate tectonics began is a very hot topic, and one which probably induces the most arguments. So there are various bits of data that we can look at to try and constrain when widespread subduction, so global subduction, which you could make an argument is the equivalent of plate tectonics, began. So something we'll start on is blueschists and eclogites. We know on the modern Earth they form in subduction channels. They're so-called high pressure, low temperature rocks. In other words, they have a very low thermobaric ratio, so temperature divided by pressure. They're those blue things here. They only appear around about 0.8, so blueschists and ultra high pressure basalts appear then. So their absence from the rock record might suggest that we didn't have widespread subduction and plate tectonics. Of course, we know from numerous studies of this very compelling, if not incontrovertible evidence for the existence of a supercontinent around 1.6, 1.7, Columbia or Nuna, and that requires significant relative horizontal motions between fragments of continental crust cratons, if you like. So plate tectonics was definitely around here. Another piece of data that has been used is looking at the metamorphic data, which I've been involved in, and you can see using a statistical analysis, which was done by Rob Holder and others just recently, you can't explain this data from around about 2.5, so this is the Neo-Archaean into the Paleoproterozoic. You can't explain this data with a single population, and you need this divergence in thermal regimes if you want, which of course is the fingerprint of modern day subduction. But I'll show you some data later that confuses me and might question even this, so who knows if this is right. And then we look at the early Earth and we can see very few data points, metamorphic data points. So, who knows what happened in the early Archaean and the Hadean based on this data. So let's deal with a couple of those points in more detail. So the Richards, Palin and White made an argument in 2015 that the reason we don't see blueschists in the Archaean, and we don't see very many of them in Proterozoic rocks, is that there is a secular change in the composition of primary crust. And that's what we've talked about earlier. The more you melt the mantle, the more magnesium it becomes. And that is, of course, correct on average. So this is a PT pseudosection coloured in for different rock types, essentially. And you can see, we don't need to go into the details, you can see the field of blueschist here is a rather narrow field. I haven't seen shown the others, but if you look, so this is drawn for a high magnesium basalt, something appropriate to the Paleoarchaean, it's argued. And if you saw one for a moor, this blueschist field would be much bigger. So I would argue the problem with this is that so those authors suggest that you're not going to get blueschists in basalts with magnesium contents above 11.2 weight%. So this is a plot of condi of various types. These top three Well, first, there are various types of Archaean basalt, doesn't matter what they are. These are komatiites. You can see there's an awful lot of basalts, more than half or around half, that have got magnesium contents less than this magic number. And of course, the answer to that is that whilst the primary crust, the oceanic crust, would have been on average much more magnesium, it differentiates much as the modern day oceanic crust differentiates. So the magnesium content of the pilolavas is much lower than those of the sheeted dikes and the layered gabbros and the cumulates. In the Archaean, when that primary crust would have been thicker, more magnesium rich, less silica rich, so it would have been less viscous and hotter and thicker, you would expect this fractionation to go to even more extreme. So the top of the Archaean crust, which is the stuff that you would expect blueschists to form of mainly, would have a very similar composition as shown here. So I think it's very difficult to support that argument that it's a compositional thing. But we don't really talk about eclogites. So here is a phase diagram, again, a series section drawn with ink. Oh, blimey, I'm getting excuse me, with increasing depth or pressure up the y-axis and increasing magnesium content along the x-axis. So this x0 equals 0. These are more black basalts, and these are much more magnesium-rich things that you might argue is stable in the Archaean. And you can see those data points of Herzberg down there. And what you see is, so this is the field of modern kind of eclogites, garnet, cosite, rutile, rutile-bearing, quartz-bearing eclogites. These are some beautiful rocks from Western Norway, and they form in morble-like rocks. When you get higher magnesium rocks, you expect, this is also a high magnesium eclogite from Western Norway, these beautiful OPX garnet clinopyroxene eclogites, which are stable in here, so much more magnesium compositions. And even if you go to the extremes, you find OPX olivine garnet, ilmenite kind of rocks, which are really, really distinct. They've also got quite omphacitic clinopyroxene. We just don't see those also in the Archaean. So whilst I can buy the argument that blueschists might not be preserved because they're quite fragile rocks, they've got hydrosphases in them, micas and amphiboles, I don't buy that for eclogites. Okay, so let's go to the water source, and we've got, again, two end member kind of options here. Where did the water come from that we absolutely need to hydrate our amphibolites to then melt them and form TTGs? Well, we have, we can either derive it from the top, from the oceans, so a top-down model. Subduction, as we've discussed, is an excellent way of doing that. Is there some other way? Or we can have bottom up from the mantle, conceivably. So I'm going to show a couple of numerical models. We don't need to worry about the details, but we're going to look at a model of some oceanic lithosphere diving beneath a continent, and then we're going to see the second continent come in. Of course, we're under the water here, so this is an illustration of a good way of getting water down. And of course, you all know how subduction works. I'm just illustrating this to show you that the numerical models, like them or not, are capable of producing really quite plausible results from very straightforward starting situations. Now, there's a slight complication in this case, in that we have to actually break the lithosphere. We have to impose a weak zone to initiate subduction. Subduction initiation is a difficult problem. But you know, this reproduces what we would see again, for instance, in the Western Nights with Baltica, collision between Baltica and Laurentia, really quite nicely. So you can make a strong argument, I think, that these models do a decent job, and that job is getting better. But is that the only way of getting water back into the mantle? So here's a very simple model that we published a few years ago. Again, a simple setup, quite a thick basaltic crust in green, a residual mantle lithosphere in blue, and the asthenosphere is in various colours of red and orange, and where it's partially molten we have yellow. I beg your pardon, this is hydrated crust at the top, this is anhydrous crust here. So what we want to get down is this green stuff, okay? And this is for a mantle temperature of 1600, very warm, arguably too warm, but let's see what happens. So remember, you're looking for what happens to green stuff. So the base of this crust is gravitationally unstable because it's denser than the underlying lithosphere, lithosphere and the asthenosphere. Those are weak, so it starts to drip into the mantle. And as it drips into the mantle, the asthenosphere has return flow, you have some decompression melting, and you produce new crust, which gets to the surface. We put all of it to the surface and hydrated all of it. Of course, that's a simplification. Maybe 10% of it got hydrated, maybe 20%. It really doesn't matter, because on the way down, it dehydrates and hydrates what is above it. So I would argue that that's a plausible mechanism of also getting the water down from the surface. However, there is this intriguing possibility that we could get some of the water from the mantle. And unfortunately, we have some very exciting new data which maybe addresses this problem, but I will get shot by my co-authors if I talk about it, so I'm afraid I'm going to have to leave you hanging. Okay, so let's look at a second model. So again, this is an even simpler setup. So this is at a warmer mantle temperatures, but we don't impose any weaknesses. So we've got a so-called stagnant lid, which is what I showed in the previous model, rather than a mobile lid, which is subduction. That's stagnant lid behavior. And we've got a very, very simple setup here of various types of basalt sitting on various types of mantle. And we impose, there's no convection here, we impose a single pixel cell within this model with a higher temperature. I think it's 10 degrees centigrade higher than the surrounding mantle, from which mantle convection automatically begins. It's quite extraordinary, I think, but I'm a sucker for these sorts of things. So let's start the model. I'm just going to scoot it on a bit. Nothing much happens, but you can see some kind of perturbations appearing, and then we can see this dripping that I talked about earlier. We can see the formation of what might be some sort of spreading ridge here, but all this recycling of the crust into the lithosphere, there's anything like subduction currently. So we're just moving on a little bit. We can see the formation of another one of these spreading ridges. We're seeing delamination of large portions of the residual lithosphere into the mantle. So here's another spreading ridge conceivably. And then I'm going to go somewhere close to the end, and then we can see that this model generates something that you could make a strong argument for that looks like subduction. So here we go. And down it goes, but it breaks off pretty quickly. It's a transient subduction event, and all these orange colours are pixels or cells within the model that are predicted to be TTG composition. So these models are quite exciting. Now there are three different scenarios that these authors described in which you can produce this TTG crust at appropriate conditions that are nothing to do with subduction. And you can also form things that look very much like granite greenstone crust and grey gneisses. And we can test them against the very few data that we have from early Archaean rocks to see if the predicted PT paths of those pixels fits what we know, and it seems to do a pretty decent job, but there's not very much data. However, so this is I find this a very interesting slide. I asked Elena Sisova for all of her data from those TTG things that were not formed by a subduction environment, and I've plotted them here. Now, a modern subduction geotherm is, so this is again pressure against temperature. These are different geotherms, obviously getting much warmer as we go down here. You can see a modern subduction geotherm is probably somewhere up here. So these are warmer, which is fine, but you can see a whole range of pressure, temperature conditions generated in non-subduction settings. And what's really interesting to me is that there seems to be a bimodality about this data. So that's exactly what we argue, this bimodality, to be the signature of subduction. I don't know what this bimodality means, but it seems to be present. So maybe all that stuff is wrong, which is fine. And coming to the end, when did the first stable continents form? So this is, let's have a look at the right-hand side here. This is a plot of TTGs, and the database has been filtered to make sure they adhere to the strict, although it's not strict at all, definition of TTG. So these are low potassium sodium ratio, they're high strontium yttrium, they're silica over 66 or something, can't remember exactly. But these are TTGs, 563 of them. You can see some characteristic peaks that we know from the detrital zircon record, 2.7-ish, 3.2-ish, 3.5. These are the age of most of the TTGs in the Barberton and the Pilbara. And of course, this data is biased by the places that are easily accessible and people like to go and aren't going to get shot in. But in terms of strict TTGs, the first ones we see appearing are 3.9, 3.8, mainly in Greenland, and then things really start to pick up after there, and we actually see them in most continents, despite what this data says later. So, is this when major volumes of continental crust started to form? So this is an epsilon hafnium against age. I am absolutely not an isotope geologist, so this is the composition of chondrite, so bulk earth, if you like, and to get to more evolved, I'm already getting into trouble with my terminology. To get up, to get to higher values for epsilon hafnium, we have to have a more radiogenic source. So this essentially is the trend that we would expect a depleted mantle to follow to higher values, and the complementary crust to lower values. So let's just look down here. So these are the Jack Hill zircons, which, as I said, go back to 4.3. Zircon it grows in rocks that are saturated in silica. We know it's in all granites that we look at. This is very convincing evidence for the presence of volumes of felsic crust in the early Earth. But of course, the felsic crust, if it was large volumes, crust has to come from somewhere. And that's what a depleted mantle is. It's depleted in the crust. So when we look at the data here, we can see that there is no evidence for any depletion. So this is a slide from Jeffrey Vort before about 3.8 or 3.9. You could argue maybe going back to 4. So this is, to my mind, extremely convincing evidence that there were no significant volumes of continental crust preserved before that. And that these Jack Hill zircons, as others have argued, probably formed in small pockets of felsic melt that formed in what was a dominantly mafic crust that was subsequently recycled. Okay, so I'll finish just with a couple of summary slides, really. So I think the vast majority of the stable and surviving continental crust started to form about 3.8, 3.9 maybe, and much of the action was over in the production of juvenile, so first processed TTGs was probably over by 3.5, maybe a bit younger. I'm not going to go into the details, but those rocks, at least in the East Pilbara, have signatures, trace element signatures suggesting they formed in this green field here. So at thermal gradients of around 900 degrees C per gigapascal, which is way warmer than subduction. I am not arguing against the subduction origin for some TTGs. I think the vast majority, however, formed in this stagnant lid setting that we touched on earlier. However, when we look at the most evolved rocks, these are the so-called eclogites in the Acasta, and these rocks are 4.03 billion years old, and they do not have anything like a TTG signature. So these are average TTGs in this grey field here. Here are the green lines of some other younger Acasta rocks. But these really ancient components shown in the red here have really elevated heavy rare earth element concentrations. Now, some people have argued that they formed in a setting very similar to or identical to Icelandites, because they have compositions that are indistinguishable from Icelandites, and that may well be the case. But I would argue that their formation is consistent with impacts, and we know there were lots of impacts from the lunar record around about this time and much older. So it's perfectly plausible, and I've not read any evidence that makes that implausible. And you can draw, you can do some models for those sorts of rocks. These green things, these green layers, are rocks that have the correct temperature based on our modelling to produce those ancient gneisses. These things are far too deep. But any of these things, which are at rather shallow levels, very shallow levels in the crust, that's where we predict partial melting to form these small volumes of that sort of crust. And having spoken to several impact experts, there is no reason whatsoever to expect that you will get any of the impactor into these rocks at depth. You might into the impact melt sheet itself, but just analysing the rocks to see if they've got elevated chromium isotopes or something, I don't think is disproving this. But I'm perfectly happy for it to be wrong. I would like to say some things about what I really think is going on in the Hadean. And we had a very exciting trip a few weeks ago, lucky us, to the Narrier terrain, and I think we might have some ideas that might be of interest, but we don't have time for that now. So I will finish by putting up a shameless plug to the Archaean symposium, which was due to run this year, a few months ago, but which for obvious reasons was cancelled. And whilst the date has not been finalised yet, the expectation is that that will take place in July 2022, where I think it's very likely that we will all be able to travel. So I would encourage those of you that are interested in things Archaean to come along to that. It's going to be held hopefully down at the hotel in Fremantle. So nice, nice restaurants, and you can go for a paddle and other things. Thank you very much for your attention.